So in this video, I'm going to be summarizing some of the stuff that we're supposed to know for basic quantum mechanics. And so we start with the Schrodinger equation. We're going to be using Dirac notation, of course, right? That's what we're trying to emphasize to make sure that you're understanding Dirac notation properly. So the Schrodinger equation is you have a Hamiltonian operator, which might be a function of time and we have a quantum state identified by the ket psi t is equal to IH partial of time with psi at t. So this is the Schrodinger equation. And specifically, we're going to be looking at Hamiltonians, right? So specifically, I'm going to be solving one of the Hamiltonians for the infinite square well and the solution for the infinite square well, but make sure that you have a general understanding of what's happening. So when the Hamiltonian is time dependent, if Hamiltonian is time independent. So if I look in the Hamiltonian, there are no t's in the function, in the operator, in the observable operator. There's no time independent, and if that is true, then we know that the evolution of the wave function is governed by the propagator times the initial value, the initial state of the quantum state. So remember, in Dirac notation, we don't really care whether we're working in position space or momentum space. So the point is that we can generally solve these problems in the abstract ket space with operators acting on the ket space. So, and remember that once you have this, the Eigenvector Equation for the observable is going to be for the Hamiltonian. I'm going to assume that the Hamiltonian has a spectrum. These are the eigenvalues. They're real because an observable is an instrument that we use to measure quantum states, and measurements are real. So this Hamiltonian operator has a spectrum of real eigenvalues. I'll label these as E1, E2, and so on. So this is the energy levels that we're expecting. So once we have this Hamiltonian, we have the Eigenvector equation. So I'm going to label this as e to the a, one of the Eigen States, energy eigenstates, corresponding to the eigenvalue of the energy corresponding to the eigenstate Ea. So we have the eigenvalue and the eigenstate corresponding to, well, this is the Eigenvector equation. So remember that, just be careful, just note that the position representation of this equation, which in this case would be, for example, x in 1D, so this is the position representation of this Eigenvector equation, right? This is sometimes referred to as the time independent Schrodinger equation. So just remember that, okay? So we can expand out the Hamiltonian operators, which I won't bother doing right now, but just remember this is sometimes referred to as a time independent Schrodinger equation. So we want to solve specifically a specific problem, and so we're going to be working on something called the one-dimensional infinite square well. This is the one-dimensional infinite square well problem. So you get to basically understand the steps in construction using Dirac notation. So that's our emphasis today. Make sure you can actually do this. And once I get a solution, maybe I'll show you the steps in reconstructing the evolution operator. So remember, this is the evolution operator or the propagator. So we'd like to calculate that in exact detail. But this is in Dirac notation. So anyway, let's go to actually solving a 1D square well. And so most textbooks in quantum mechanics, they tend to go into position representation, and we're actually going to be doing it in terms of Dirac notation. Dirac is more flexible and it's more abstract, and there's a lot of derivations that might not be familiar to you, but hopefully. So in the 1D infinite square well, 1D infinite square well, what we're looking at, right, is basically a potential where we have a particle, and let's say this is the x-axis, and the particle is trapped between a little box and a one dimension, right? So we have a mass particle m, and so we can construct a particle. This mass is basically bouncing back and forth. We want a quantum description. So we'll construct the Hamiltonian, and I'm just going to skip some steps. Okay, so I'm going to assume that when it bounces, the total energy of the system, the Hamiltonian, in classical mechanics, right, is p squared over 2m, the momentum squared, which is 1/2 kx squared, right, x dot squared, the velocity squared. Anyway, so we're constructing the Hamiltonian operator corresponding to the quantum mechanical operator associated with this, and we're going to get this as p squared. Remember, when I'm putting the hats to remind you that we're doing operators, and so I'll tend to do this for a while unless I forget, which when I'm doing some long derivations I tend to not put out the hats all the time, but hopefully you'll catch my mistakes. So here's our Hamiltonian, and our potential is equal to plus infinity when x is not in the interval from 0 to L, and equal to 0 if x is an element from 0 to L otherwise. Okay? Okay, so we've constructed the classical model, constructed the quantum mechanical model, and so first couple of things we'd like to calculate so our purpose is we're trying to notice the Hamiltonian has no time dependence, so we know that the evolution operator is actually e to the ht over IH. Okay, so we know the evolution operator is going to be written like this, but so we're actually solving, so I'm going to assume that the Hamiltonian has a spectrum of E1, E2, dot, dot, dot. And we're going to be solving the Eigenvector Equation. So we're solving the Eigenvector Equation, which in the position representation, right, is the 1D Schrodinger Equation. It's time-independent Schrodinger Equation, I'm sorry. It's the time-independent Schrodinger Equation. So I'm going to take this equation, and so I'm going to do the steps, make sure that you're understanding Dirac notation properly. So let's go through the steps. So here is x. We're projecting this equation into position space. So we're projecting into position space. Which is really x space. So I don't feel like writing a lot. It's kind of late tonight. Anyway, so H energy eigenvalue is equal to x and EA. So here's our first step. So next step is that we're going to take this x and we're going to write p squared over 2m. And EA is a constant, so we pull that outside. So remember what this means. What this means is that we're looking at the eigenstate projected into position space. We're actually looking at the projection of the nth energy eigenstate projected into position space. We could have used P, but this equation actually is the Schrodinger equation that most people, most authors, most textbook authors refer to. But we're using generalized quotient. Just make sure you understand that EA is a function of x now. So this is a function of x. So the first thing we should notice, right, is that x, the projection operator, the momentum operator projected into position space, right, is h bar over I partial of x. So this is This is the rule that we'll be using. It's in my course notes already, so hopefully make sure that you remember this rule. So you're projecting the momentum operator into x space. And so we know that this becomes this. So we'll pull out the 2m, so this is 1 over 2m. Let me just double check if it's on the video. Yeah, it's still on the video. That's good. X operator P EA is equal to EA X EA. So we're going to apply the bra, so we're projecting P into the x space, and so we're left with 1 over 2m, and we get h bar over I partial of x. So this is our first projection and acting on P again. So hopefully you're getting used to this Dirac notation. So here's our Dirac notation, and I need to erase everything, but before I erase the top half, I just want to make sure you understand. So we're assuming the particle lies between 0 to L, right? So we're expecting that the position, the projection of x lying in this interval is not going to be 0. And because the particle is not here, the quantum, so this is the quantum amplitude, which from 0 to L can't be 0, but we're expecting the quantum amplitude to be 0 on the, is it on the video? Yeah, it's on the screen. So we want the quantum amplitude to be 0. So the particle is only found from 0 to L. So L is the length of the box. Okay, and again, we're expecting the, so remember, these are functions. So maybe I'll rewrite this later in a sec in terms of things that normally not you see in most textbooks. So this is the projection of EA into the x space, and this x space, right, is equal to 0. So the quantum amplitude of this energy eigenstate, right, when x is greater than L is 0, when x is less than 0, it's equal to 0. And what I'm going to do is basically, even though it's 0, we're actually going to try to make the quantum amplitude continuous across this boundary mark between these two boundaries. So I'll say that the solution of x e to the a at these boundaries is 0. Okay, so anyway, so we're getting there. So once you've understood this, let me erase the top half because I don't have a lot of space. It's not like we have tons of board space. So this is the equation I'm going to be working with down here, and this is the Schrodinger equation. This is the time-independent Schrodinger equation because remember the Hamiltonian is time-independent and we know the evolution operator. So let's go through that. So let me erase the top half. So again, look at top. So we're projecting the P operator into x space, and so we'll have, so I'm going to erase this. Our next derivation is that it's continuation, right? So we have h bar over I partial of x, and the projection of the momentum operator into x space gives you another h bar over I, and then we're left with e to the a, and that's equal to the energy value, the energy eigenvalue of x a. Okay, so I'm going to take these hi, these are constants, right? If they fall apart, they pass through the partial derivatives, and so you're left with minus h squared, I squared, over 2m times the second partial derivative of x squared of x EA equals EA. So just remember, when we have Hamiltonians, right, that are time independent, and the Schrodinger equation, just a little note, just to make sure you're really emphasizing this, okay, that in the position representation is sometimes referred to as the time-independent Schrodinger equation. Okay, so a lot of textbooks, so you might have seen this in your textbook as just a function like phi of energy eigenstate of x, and this is a phi of x. But we're getting used to Dirac notation, so I'd prefer if you didn't do it this way, because we really want to reinforce Dirac notation in this class. Okay. So basically, how do we solve this? It's a second order differential equation. So just a little side note if you forgot. And if you, hopefully, so I'm going to erase this at the bottom. Just so remember, if somebody gives you a second order differential equation of, so let's say I have a function y dx squared is equal to minus omega squared y, second order differential equation. We know the solution, right? There's is equal to y is equal to a cosine of omega x plus b sine omega x. Or we can actually, so where a and b are two constants that will be specified by boundary conditions, so here's your two constants. It also can be specified by a constant c times sine or cosine, it doesn't really matter, and plus a phase constant d. We can actually select either, but for simplicity I'm just going to stay with this because a and b are separable instead of using a double angle formula to separate things, which is more time consuming. So I'm going to assume that the general solution for a second order differential equation is this. Notice this is a second order differential equation. Even though we have partial derivatives, these are functions of x, so this becomes a second order derivative in x. So it's an ODE, not a partial differential equation. So let's erase this. So we got the general idea. Convert this into a more form that you can see it. So I'll convert this into a total derivative. So you got to get used to the habit of thinking that this is a function of x. This is a function of x. We're projecting the eigenstate, the 8th energy eigenstate, into position space. We're going to move the 2m over here. So it's a minus 2m energy eigenvalue and h bar squared. So this is our general solution for omega. So we can actually call this, and so we know the solution for this, right, is going to be something of the form that the eigenstate, the 8th energy eigenstate projected into the x space is equal to some constant times sine of omega x plus, plus b cosine of omega x. Okay, so a and b are to be constants to be found. A and b could be complex, but I'll have to show you a derivation to make sure you understand that the functions for one dimensions, right, are actually can be considered as, these eigenstates can be all considered as real, and we can absorb the quantum, the phase factor, right, into the time factor. So I'll discuss that some other time. But right now, let's just assume that I have the solution. So all we know is that x at EA, as x approaches 0, this is the left-hand side of the infinite square well, right? That's equal to 0. And so that's when x is equal to 0, so that's equal to a sine of omega times 0 plus b cosine of omega times 0. Okay, so we know that this term is 0, and so you're left with that cosine omega 0 is 1, and so you're left with that derivation that says that b, is this on the board? Yeah, b is equal to 1. So we simplified that the the left boundary condition, right, when x is equal to 0, when the particle is not to be found when x is less than 0, the left-hand side of the box is equal to 0. So we're just making sure that the quantum amplitude is continuous from minus infinity to 0, from 0 to L, from L to infinity. So we already found that b is equal to 0. Okay, so we've now reduced this problem, so I'm going to erase this a little bit. So we've reduced this problem to b equals 0, so this quantum, so one of our boundary conditions has canceled one of our b values, so we don't have to worry about that. Our next problem is that we have to solve for a, and now I'm going to use the right boundary condition, that as x approaches L, then that's also equal to 0. So we have a sine of omega L is equal to 0. And you might think that we can set a is equal to 0 also, right? But if we did, then the quantum amplitude of the energy function in the position space is going to be 0 everywhere. And if it's 0 everywhere, the particle does not exist, so we can't have that. So for that to happen, right, the only way that this could be 0 is that a cannot be 0. A cannot be 0. If it was, then the wave function would be, the quantum amplitude would be 0 everywhere and the particle would not exist. Okay, so it can't have that. So yeah, so the only way this can happen, right, is that if sine of omega L is 0, so this actually leads to the quantization. So omega L must be n pi, where n is an integer. Can you see this? Yeah, n is an integer. It's 0. But and we have one more value. N can't be 0. If n is 0, right, then omega L would be 0, and then sine of 0 would be 0, and then we don't have a quantum amplitude. The quantum amplitude is again 0. So n can't be 0, so you're left with that n can be minus all the negative values, positive values, but not 0. So n cannot be equal to 0. It has to be an integer, but it can't be equal to 0. Okay, so this identification means that omega will identify this omega n is n pi over L. So I'll write this box, and I should write these equations down, so I don't need the top, so I'll write these equations down on top. Okay, so the first equation you should get from quantization is that the nth, so for some reason there's quantization, and that omega n is equal to n pi over L. And n is an integer, and n cannot be equal to 0. It cannot be equal to 0. So we've gotten that far. Okay, so now we've kind of reduced this. So let me erase this and summarize so far what we've done. So we've just said that the eighth energy eigenstate is given by a sine of omega nx in the interval from 0 to L. It's 0 everywhere else, but from 0 to L. Now we also, the nth energy state, we can identify the nth energy eigenstate with the e to the n. So instead of calling it e to the a, let's call it e to the n. And so we have another equation, so we know this is omega n squared, so this is 2m e to the n over h bar squared must be equal to omega n squared. This is a solution from the second order differential equation, right? So that's omega n squared. In this case it happens to be, so I'll summarize these in a sec, but we need to do calculations on these. So this is h bar squared omega n squared over 2m is equal to the energy value. And we can substitute omega n already, right, n pi L. So if we do that, then we get h bar squared over 2m omega n is n pi over L squared. Okay, I won't reduce this because it's not relevant. I'm sure you can play around with like reducing it to n squared pi squared over L squared. That's not the difficult part. So let's not worry about that. So let me erase this, and we still have a normalizing constant to find. We don't know what the value of A is. So let me summarize this so far. So far we have that the x to the n is a to the n. I think I wrote it down here already. Yeah, I did. So I can erase everything over here. Okay, so our next step, right, is we need to find the value of this a, so we can actually do calculations and expectation values of different operators. So the first step we're going to do is that I'm going to ask myself, what is e to the n? And that's the, so we know that from Dirac notation, right? We showed that. So it's asking, if I'm in an energy eigenstate e to the n, and I try to make a measurement of e to the n, right? So the quantum amplitude I'm getting, right, has to be, the square of it must be equal to 1. And we usually take this to be Kronecker delta of 1, 1, which is equal to 1. There is a phase factor that I didn't really mention, but it's in my course notes. That phase factor, right, can be dropped. And so effectively, this mathematics, assuming it's equal to 1, is fine. So, but what is that equal to? So what I'm going to do is I'm going to use a closure relation. So remember, this is, so you have to really get familiar with the closure relation. And so we have two spaces to work in, and there's a Fourier transform. So we have working in position space and momentum space. And we have Fourier transforms to go back and forth between the position space and momentum space. So we have to calculate, make sure you understand. So here is e to the n, and times 1, but here's my closure relation. So here's my closure relation, dx, taken from minus infinity to infinity, that's our closure relation of e to the n. So hopefully you remember this is the closure relation. So e to the n projected onto here, we get x is equal to minus infinity to infinity of en x en dx. Notice we can do that because these are not functions of x. These operators have nothing to do with x. They squeeze in, and suddenly we have two functions which are functions of x. Also, we know that these quantum amplitudes, right, are 0 from infinity to infinity, so I can actually reduce this. And because I'm running out of board space, I'll be erasing a little bit so I don't use up too much space. So we know the quantum amplitude for x less than 0 and x greater than L, right, is equal to 0. And so the quantum amplitude, right, so we can actually integrate from only from 0 to L instead. So remember, our closure relation says that this is our closure relation. That's equal to 1, right? So this is equal to 1, a closure relation. So now, so remember what this is. This is really going through these steps to make sure you're really emphasizing these concepts, okay? So x en conjugate, or Hermitian conjugate if you put it in the operator notation, but we're doing the conjugate of x en dx. And so this integral, right, is, so I'm assuming these are real values. So if these are real, which I haven't shown you, that we can always treat this by looking at the, saying that for one dimensions, the quantum amplitude can be taken as a real function. We don't have to worry about being complex because the complex phase factor, right, can be absorbed into the time. But it's in my course notes, but just let's go to the details on this later. So it's real. So A is real. So this equation now becomes from x is equal to 0 to L. This is all equal to 1. Remember, this is equal to 1. This is equal to 1. For a squared times sine squared, and I'll put this as omega nx dx taken in. Okay, So we have to solve this integral. So remember the standard formulas that we have to solve. So I don't want to erase anything, so I guess this has to go on top here. Let me erase this out. So note that the standard formulas you should make sure you understand, right, is that if somebody gives you something like x squared, that in terms of the double angle formula, it's equal to 1 plus cosine of 2x. I should maybe do it in terms of theta. Yeah, I think theta sounds so much better. Okay, and you should also memorize that n squared theta is equal to 1/2 1 minus cosine of 2 theta. Okay, so we'll be using the sine squared formula, and so I can write this out as x is equal to 0 to L of a squared, and I can pull out the a squared, but I'll just leave it in for now. 1/2 of 1 minus cosine of 2 omega n, and I'll actually substitute omega n here. Omega n happens to be right, where is it? Here we go. Oh, I didn't actually write it out. Oh, here we go, on top right here, n pi over Lx, twice this angle, and let's close the parentheses, dx. So if you look carefully, right, we're going to be integrating a constant and integrating a cosine. Integrating a cosine, we should be getting a sine, and that sine function is periodic of 2 pi. Notice that we'll be integrating from 0 to L. So 0 to L, right, we'll have a period that cancels, so it'll be a multiple of 2 pi. The net effect is that this, if you think about it carefully, this whole term, right, will be 0 in the integration after integration. So we don't even have to worry about it. And so we're left with 1/2 a squared integral, and the integral from 0 to L is L. So we're saying that this is really a squared over 2, and the integral from 0 to L is L. And that's equal to 1. Hopefully I didn't lose anybody. So it's a squared L equal to 1. And so, this is on the board? Yeah, it's on the board. And A is equal to 2 over L square root. There is a plus or minus. I'm not going to worry about it because we don't measure quantum amplitudes in quantum mechanics. What we measure is the probability. So if you remember our postulates, right? So postulate number 1 is a quantum state, existence of quantum state. Postulate number 2 was the measurement of observables. And postulate number 3 is the Born lemma. So there's the postulate number 2 is the wave collapse. Postulate number 3 was the Born lemma. And postulate number 4 is a Schrodinger equation. And postulate number 5 is the de Broglie equation, which I'll explain later. But so those are the basic 5 postulates we started off our quantum class at day number 1. Started off our class with. Okay, so so we take this, and so let me substitute this in and start working with this, because I want to make sure that so our quantum amplitude A now has the factor fixed. So now we're all set. And omega n might as well, I can just leave it in, because I hate writing this over again. Okay, so anyway, so we got up to here, and so this summarizes everything that we need for the quantum infinite square well. So let's do some calculations and show you, so I do expect you to make sure that you can do these calculations. So let's calculate the expectation value of let's do a simple case of the expectation value of the nth energy state with the position operator. So how would we calculate this? So again, so we're trying to get used to Dirac notation to make sure that you're getting familiar with Dirac notation. So here is the expectation value. Now we know that, as I mentioned in class, the Eigen States, right, of the infinite square well, and I'll actually draw them out. the quantum amplitudes, right, from 0 to L are basically, they look like this, the first eigenstate, and then the next eigenstate, and I don't think I can do this good enough, but so these are the eigenstates in the position representation. They look like sine waves, so they look like nodal points, right? So you'll have the first one has no nodes, next one has one node, two nodes and stuff, and so on. But the main thing is that we have to make sure, so on average, right, we expect that the particle by symmetry, right, that the average expectation of the position operator, right, should be the middle of the box. In this case, it should be L over 2. We can confirm this, but the calculations will be a little bit long, but we know that, but we have to make sure you can set up these integrals. So I'm going to sandwich, so I need to convert this Dirac notation into an integral that I can calculate and evaluate. So I'm going to hit the closure relation right over here. I'm going to use the closure relation for position. We're not working momentum. We could. And so we're left with En. I'm going to use the closure relation over here, delta x. And remember the closure relation, okay, is actually from minus infinity to infinity. Be careful, okay? Only later, right, do we say that it's actually, once we squeeze in, then we say that the quantum amplitude is 0 from 0 to L, from less than 0 and from L to infinity. So here's our x operator and e to the n. So this is my closure relation that's set to equal to 1. So next calculation, I'm going to absorb this in. Notice it's not a function of x, so I can do that. I can absorb them and use the Dirac notation. So x is equal to 0, infinity to infinity, en x, and then we have x operating on x. Remember, this is not a function of x, it's an operator. There's no variable x in here. Once I absorb it in, right, then we can do some calculations here. So make sure you're getting these steps, okay? It's very important that you understand Dirac notation to do more advanced quantum mechanics. So make sure you're understanding Dirac notation. Actually, I'm going to be lazy, so I know that this is the quantum amplitude conjugate, right? And so it's we know it's going to be 0 from minus infinity to 0 and from x greater than L. So we know that, so I can reduce this integral. This is 0, so I'll reduce the integral from x is equal to 0 to L. And so the projection of the x operator onto x space, right? So I'm on a little side note. The projection of the x operator into x space, right, is given by x, the eigenvalue x, and remember, this is only true when we are working with operators that I can do these calculations, right, because these operators are observables. So otherwise I'll have to use x conjugate, but these are real values, so that's why I can pull out the x. So this is now, I'll actually write this in en conjugate. So this is now x and projection into enx. And so we're already expecting an answer of L over 2. And so we have the conjugate of this. So this is actually, so this is this function conjugate, which is the same function. So I can do some of these calculations. Hopefully you can see the steps. I'm not going too fast. So it's square root of 2L times square root of 2L. You get 2 over L. And then the integral taken from x equal to 0 to infinity. Sorry, my mistake. 0 to L. It's late. Okay. So here is sine squared. And omega n is n pi over L. And then don't forget the x over here, which is this integral. So we have a little work ahead of us. The basic procedure is that we'd solve this integral, and you use our formula, which I erased, but remember this is equal to 1/2 1 minus cosine of 2n pi x over L. And so we'll have like x times integral. So anyway, go to do the calculations, and I'm setting up the integrals because that's what I'm really emphasizing. So hopefully you're going to use SimPy to do the calculations to make sure. So to double check these integrals, right? Nobody wants to waste time doing this long calculated integrals. Okay, make sure you can actually do SimPy and do symbolic computations, do these calculations. Anyway, you'll find that the answer is L over 2. So let me erase this and let's do another calculation. So because I'm really emphasizing Dirac notation because that's what you need to understand. So let me erase this. So, and let's do an expectation value. I'm doing an expectation value of the nth energy eigenstate sandwiched, and let's say that we'd like to calculate the average momentum. And En. So this is what I'd like to calculate. So again, I'm going to do a closure relation. And we have absolute x, the Ketbra dx. X is taken from minus infinity to infinity. Hopefully, yeah, this is a painful process. Hopefully you can do this a little bit faster, but right now I just want to make sure you can actually do Dirac notation properly. And forget the p operator. Okay, so we have this, so I'm going to pull out the En into x and the projection of the, oops, yeah, that's correct. Okay, so this is now, x is taken from minus infinity to infinity, and En x, and x sandwiching the momentum operator in x position to e to the n dx. So first thing you should notice, again, I'm running out of space, but hopefully you'll get through this. We know that it's going to be 0 when x is less than 0 and 0 when x is greater than L. So we know that the integral, right, evaluates down to just the integral from 0 to L. So we reduced it to this. And so the projection of the momentum operator into x gives you, and actually let me just put the conjugate in so you can actually see this better. But remember that these are real functions, so the conjugate of this is the same function as 2 over L sine, so it's no conjugate. So this is now h bar over I partial of x times the momentum operator. So this is the projection operator. Sorry, so we're projecting the momentum operator into x space, so we get h bar. And this is kind of really late tonight, but I said I would make the video on the weekend, so sorry. Late, better late than never. And so this expectation value is a derivative. So finally we're expecting to calculate an integral. I'll pull out the h bar over I and integrate from x equal to 0 to L of, let me, actually, you know what, let's just do everything in one shot. I'll set up the integral. Yeah, I'll just set up the integral. Okay, so h over I comes out, and the x to the n is 2 over L, but there's a 2 over L over here when I take a derivative, so that's really 2 over L. Integral taken from x is equal to 0 to L. Is this on the board? Yeah, it's on the board. Okay, and then we have sine of n pi x over L times the derivative. I'll just take a derivative of sine of n pi x over L dx. And actually, we can, if you're kind of lazy and you feel like just crossing these out, dx's, hopefully you're going to be typing this out in SimPy so you don't waste time doing these integrals, but you can do this by hand. Notice there's a sine of n pi x, a sine pi x, so this is actually 1/2 sine of n pi x squared L squared. So I know the integral, but I know that from 0 to L, this is n pi, so that's 0. So this whole term is equal to 0. So the average expectation of the momentum operator is going to be 0, which is expected, right? If the particle is just as likely to go to the left as the particle is going to the right. So the net effect is that the wave function expectation value of the wave function momentum is going to be 0. Okay, so we can actually do this analytically, but I don't want you to spend time doing analytical equations. I want you to plug it into SymPy and do this symbolically so you don't waste time doing calculations. But for this, I think it's pretty straightforward. Okay, so let's do another calculation. So let's calculate the observable Hamiltonian H. We can actually set this up. What is the average expectation value in the nth energy eigenstate? So the nth energy eigenstate, well actually we already know the answer to this because this is the, so if you look at it right, this is the Eigenvector Equation, so we know the answer. Pulling this out, so we're left with e to the n, en, en, and this is Kronecker delta 1, 1, so this is e to the n. So we're expecting that the average expectation value of the energy observable, remember an observable is an instrument for measuring, it's a measurement instrument. So an observable, we have a measurement instrument that measures energy. So that's what the Hamiltonian operator is. So once the Hamiltonian is, so the average expectation of energy for a system that's in the nth energy eigenstate is the nth energy eigenstate. Okay, great. So we already know this, but I'd like to set this up as an integral to make sure that you understand how to set this up in position space or momentum space. We're choosing position space because I just happen to have the eigenstate in the position space. So I'm going to do a closure relation over here. And I think that's enough for tonight. Actually, I'm going to be lazy. Okay, yeah, I'm lazy. I was going to just skip steps, but I think I better not. So here's our, I'm skipping steps, sorry. So this is the Hamiltonian operator times e to the n. So we already know it's equal to e to the n, but what's the integrals that you're going to be setting up? So this is our Dirac notation, so we can actually convert this into an integral equation in position space. So squeeze in this integral. Sorry, squeeze in the bra. And x, and if you remember, Hamiltonian operator is p squared over 2m. Can I see it on the board? Yeah, p squared over 2m times e to the n dx. And we know that this is from 0 to less than 0 is going to be 0, and this quantum amplitude conjugate is going to be 0 from less than when x is less than 0 and x greater than L. So I'm going to reduce this integral from 0 to L. And x acting on p brings out hi partially, doing it twice. So we're actually setting up an integral that goes from 0 to L of en conjugate. But remember, this is already real. It's not. There's no complex portion. So this is the same function times h bar over I partial of x. You do it twice. So projecting out twice, and don't forget the 1 over 2m, so I'll pull out the 2m. I'm skipping steps, I know. And x en dx. Okay, so this becomes minus h squared over 2m integral 0 to L of, let me do it on the board. Okay, so we have 2 over L, so the 2 over L comes out, so 1 over 2m, there's a minus h squared, so I'll leave that minus h squared, and then there is a 2 over L coming out there, because we have it twice from here and here. And so we have now an integral that 0 to L of sine of n pi x over L, the second derivative of sine of n pi x over L dx. Okay? Okay, so when you calculate this, right, you'll actually find that eventually, right, you'll get back the energy, the nth energy level, which in this case is going to be equal to, what is the nth energy level? Right over here. So it's going to be, so remember, you can do it by hand, but it's really time consuming, but I'm really expecting you to be able to type this into SymPy and do symbolic computations. A lot of these integrals, they're very complicated and nobody has time to actually do them by hand. It might be a fun experience if you're like taking the subway or something and you have a half an hour to kill. Go ahead, but I expect you to be able to write these integrals and put it down into SymPy in Python and stuff, and then calculate. So we'll actually see that eventually you'll get an answer which is h squared. This is m. So your symbolic calculator, your CAS computer algebra system, SymPy, the package SymPy in Python, is going to give you back this energy level. Okay, I think that's it for tonight, to make sure that you have a basic understanding of what's expected of you for solving, setting up Dirac notation. Okay, and so I'll put up some more videos for doing more complicated Dirac notation. Oh, actually, did I forget anything? Oh, yeah, actually, maybe I will say it. Just to remind you, so we did this calculation, right? And so we know that the Hamiltonian is broken up into, so let me erase this just to remind you. So I'll put these steps in just to make sure you understand. Okay, so when it's time-dependent, independent Hamiltonian, the Hamiltonian, right, in terms of the eigenstates, right, is given by A is equal to, let's call it n, 1 to infinity. Did you notice that n didn't matter if it's plus or minus, because when you square it, the energy level is hidden, so we don't have to go from 1 to infinity. So e to the n, e to the n, e to the n. So this is the nth energy eigenstate. So the Hamiltonian can be broken apart in terms of Ket and Bras for the nth in Dirac notation. And we know that the evolution operator, right? So the evolution operator is given by h bar t. Actually, let's write this again. The Schrodinger equation, if t is time independent, right? So the Schrodinger equation is given, the solution for the Schrodinger equation is given by this. So here's our, so psi at t is equal to e to the ht over IH psi at 0. So if this is in some superposition state, some initial quantum state, time t equals 0, it evolves, and this is the evolution operator. So I'd like to go over the evolution operator and expand it. So let's go over to the evolution operator. The evolution operator, actually, so this is the solution, this is the evolution operator, or the propagator. Or the evolution operator. Okay, so this is the Dirac solution. So this is only for Hamiltonians that are time independent. Okay, so when we do time dependence, right, there's very few problems we can actually solve in time dependent Hamiltonians, but It's in my course notes anyway, but let's go through this. So I would like to expand this in terms of the energy eigenvalues and then put it back into the Hamiltonian, the infinite square well to see the evolution. Can I erase? Yeah. So let me erase this and take a look at the evolution operator. So here is the evolution operator. And I'm going to write this as the exponent of the Hamiltonian operator and T and IH. And I'm sorry, I just, yeah, actually it doesn't really matter. So this is the exponential. I'm just rewriting it in a different way. So the Hamiltonian operator, right, can be written in terms of the energy eigenstates. Let's call this I is equal to 1 to, let's call it A, 1 to infinity of e to the A, e to the A, e to the A times time over IH. So this is your Hamiltonian and expanded. And if you kind of remember that we discussed polynomial functions of these eigenvector expansions, and you'll actually see that this can be pulled out, and you'll actually see that this is equal to A is equal to 1 to infinity, and this becomes e to the A times e to the EA T over IH e to the A. And this is the propagator. So e to the H T over IH. Okay, so that's our evolution operator. So here's the evolution operator that takes any eigenstate. And I made a mistake. This is a bra instead of a ket. So I've pulled out the bras and kets out. So we have an evolution operator. So the full expansion, right, of this evolution operator in terms of for any state is then given as, so this is a very generalized question statement. So the evolution of any quantum state is governed by, in terms of the eigenstates, the energy eigenstates from 1 to infinity of the and I'll put the, because this is just a constant, I'll pull it out. So I'll actually put it, actually, you know what, I'll put it in front. Makes it look nicer. So this times, so this is our evolution operator, which I kind of reduced it into this form, times psi at 0. So what you're saying, right, is, and we can project this into position space or momentum space, since we already know in position space what it is, right? I can project it into position space and expand it out. So let's do an example of this just to make sure that you understand. Yeah. So once I project this into position space, so this is the evolution operator projected into x space. So x projected onto, this is a constant, gets pulled out. So we're looking at an integral. A is equal to 1 to infinity of e to the A t over IH. So this is the full evolution of a wave function. So we take the initial state, project it into the eigenbases, the energy eigenbases, and these quantum amplitudes we multiply into the quantum position amplitudes and times an exponential, and this is the time evolution of the system. So yeah, hopefully this is not confusing you, but basically you have to get used to Dirac notation a lot to read papers in quantum mechanics. Anyway, hopefully I think that's enough tonight.